Today's poser. Let's consider heat energy. Increasing the temperature of 1 kilogram of water from 10 degrees Celsius to 15 degrees Celsius takes how much energy compared to the energy required to increase its temperature to 15 to 20? Question 2. Increasing the temperature of 1 kilogram of water from 10 degrees Celsius to 15 degrees Celsius takes how much energy compared to the same increase for 2 kilograms of water? So for question 1, increasing the temperature of 1 kilogram of water from 10 to 15 and from 15 to 20 requires the same amount of energy. Remember that the amount of energy is proportional to the number of degrees that's changed. Question 2, increasing the temperature of 1 kilogram versus 2 kilograms. Well, 1 kilogram requires half as much energy as 2 kilograms. Again, the amount of energy is proportional, in this case, to the mass of water. Alright. Hello everyone. This is SPH3U. I'm Mr. McBrien, and today we're going to talk about latent heat. Now we talked about the equation Q equals mc delta T yesterday, and we used it to solve the problems before this class. But this equation only works in certain carefully chosen cases. And you may have noticed that the examples we used yesterday were chosen carefully to keep water between a certain range of temperature, to only put certain materials into our flask when we were changing the temperature, when we were measuring the change in temperature. If we see a change in state, that equation no longer applies. So let's consider this situation where we have a change in state from crystalline solid to liquid to gas. And we have a graph of the heat added on the x-axis to achieve a temperature change on the y-axis. And you'll notice that as we start as a solid, as we add heat, the change in temperature is a straight line. In other words, the change in temperature is proportional to the amount of heat added, as we'd expect from our equation. And then we have a discontinuity. What's happening? Well, the solid is melting. And as it melts, we keep putting in heat, but it doesn't get any warmer. And we move through and the solid melts and melts and melts. And then as soon as we've melted all of that solid, our temperature again starts going up as we add in heat. And once again, our heat energy equation applies. We get a straight line. The change in temperature is proportional to the heat added until we hit the boiling point. And when we hit the boiling point, again, the temperature stays constant. And we have to keep adding in heat, and all we're accomplishing is, of course, boiling. And then we move all the way through, and the pan boils dry. And now we're heating the gas, and again, our heat energy temperature equation applies. Now, if we wanted to take heat out and move from a gas, the exact same process occurs, but in reverse. Now, it's worth noting that this graph is not easy to digest the first time. It's worth taking a few minutes, pause the movie perhaps, and have a look at this graph and make sure that you're comfortable with it before we move on. Okay, so of course, because we're scientists, we want to be quantitative about anything we do. And of course, we want to make some cryptic description for it so that people who haven't taken the classes we've taken don't understand what the heck we're talking about. So our term for this stuff, this extra heat, is latent heat. And so if we want to talk about changing a material state from solid to liquid, we'd call it latent heat of fusion. And this heat of fusion, no great shock, is different for different materials. So the energy is proportional again to the mass and to a constant, not unlike that C, heat capacity, but this is the latent heat of fusion. And so that latent heat of fusion defines how much energy we're going to have to put in order to melt something, and how much energy we can get back if it freezes. And you may have noticed that in the springtime, long after temperatures are above 0 degrees, there's still snowbanks on the sides of the roads and big piles of snow in parking lots. Well, this latent heat of fusion is why. Even though the temperature is higher than 0 degrees, there's a lot of heat that's going to have to come out of the air, out of the ground, and from the sun in order to do all that melting of all that ice. No great shock, since we had a flat region on our graph for boiling as well. We have a latent heat of vaporization too. And of course it's a different constant associated with that, but really it's the exact same idea. So we have a heat that's required to boil something that's proportional to the mass and proportional to its latent heat of vaporization. So take a second, have a look at this graph, and decide what words get put in here. So when a material evaporates, heat is absorbed. And when a material condenses, the heat is released. And this is no great shock, right? That heat absorption when it evaporates is the reason why sweating works so well. We cool down because the process of the water evaporating pulls heat energy from our skin. Okay, so let's take an example. How much heat must be removed from 10 kilograms of water at 80 degrees Celsius to cool it to ice at negative 30 degrees Celsius? Now the best approach to this is to actually take this problem and work stepwise. So we need a few things. We're going to build a timeline, not unlike the graph we looked at previously, and we need a bunch of different numbers to achieve our goal of finding out how much heat must be removed. So we first take the first step where we have to cool that water to 0 degrees. So we started at 80 degrees. We did this calculation yesterday. We simply calculate the heat energy. It's proportional to the mass, the change in temperature, and to the heat capacity. So we find that it's 3.36 times, sig fig error there. So call that 3.4 times 10 to the 4. So this gives us the heat required for step 1. The next step, we need to take that 0 degree water and freeze it. Well, we learned how to do that. We can do it again here. Take the heat of fusion times the mass and get 3.3 times 10 to the 4 joules. Now we've got ice at temperature 0 degrees Celsius, but we still need to cool it 30 degrees. Well, we know how to do that as well. The heat capacity of ice times the mass times delta T. And we get 6.3 times 10 to the 3 joules. And all we have to do then is just add these numbers up. And we get 7.3 times 10 to the 4 joules. Now, one thing that's kind of interesting here, it's worth noting that it took just as much energy to melt that ice as it did to take the, well, you can take it either way you want. We got just as much energy out of freezing that ice as we did out of cooling it from 80 degrees all the way down to 0. So this gives us sort of an idea of just how much energy is tied up in liquid water that we can pull out if we want to. Okay, so please try a few of these problems on your own. The textbook questions are here, and have some fun. And don't forget that each step in the process needs to be treated individually. Thank you and have a great night.